This is about uroot, which is you can read the title. It's an embeddable firmware system, although actually we have uses that apply to root file systems as well. It actually is a project I started a couple of years ago and then left on the shelf. And then about a year and a half ago, I tried to build ONIE, which involves building BusyBox, which involves a config script, which involves probably 50 or 60 different kinds of failures that always come with building C programs nowadays that involve, libtools. So I thought there's just got to be an easier way to get to bin utils I can use, and pulled this back off the shelf, and Andrey and I kind of beat it into reasonable shape. So that was sort of the beginning, was something that I can use that's not something like BusyBox, that's simpler. So I'm going to talk a little about what it is and how it all works. And I think if it were just purely a bunch of little bin utils widgets to replace BusyBox, it wouldn't be super interesting probably for this crowd. But I think the thing that makes it a little more interesting is that a lot of it involves using Go AST package to build Go. So we do source-to-source transformation using Go. And we go from things I call Go fragments to actual running programs. And when we add a build into the shell, we don't actually just add a build into the shell with an interpreted language. We just build a new shell. And that takes a couple of seconds, and then you're running a new shell. So I think part of the interest of this is the fact that we're doing source-to-source transformation using Go itself to produce things. We produce them on demand as you ask them, and they're running very quickly. I've got a Docker image, which you can use to try out last October's version. So if you want to give it a shot, let me know. It's got everything in there. You can actually core boot the firmware build. You can boot kernel with an init ramfs and see how that works. And you can use the README, which starts up in a few seconds. So uroot's a root file system in source form, as I mentioned. Anytime you type a command like date, it and any package it needs get compiled, dropped into /bin. Bin, by convention, is in ramfs. So it drops it in ramfs. Next time you run it, it's instant. The first time you run it, it's about half second. It's kind of the ultimate delayed binding. So a lot of people like the idea of having .so this and .so that. We go a little further. You start from the source, you build it, and you're done. So it's about as late delayed binding as you're going to get. There's a few variations on this theme. More of that later. But the key idea, except for the latest variation on the theme, is the packages and commands are always there as source. We don't link in any C libraries. So when you see the Go is what you're running. We don't bring in lib something.so that we didn't compile. Now, everybody's saying you're lying because there has to be a binary, and that's true. I'm lying. There has to be one binary. There has to be a init, right? There's always a binary somewhere to get your machine started. And of course, there's the Go toolchain, and that's 4 binaries. So, yeah, I've got 5 binaries. It's not completely source. Now, how do I get from typing date to getting a runnable date? Well, there's a little trick we play that I'll show in a few slides. But basically, there's a program called the install command. That's got to be compiled, but that's there as source, and init compiles it on boot. And there is a shell, but that's actually there as source, and the shell is compiled on boot and run. The init, finally, is pretty minimal. It's 206 lines of Go. So not a ton of stuff there. It's really an all-source root file system. We're not going a little too far with the hubris here, but U stood for universal. You can actually build a single flash or SSD or USB device, plug it into anything that supports the Go toolchain or Go compiler, and boot that machine using this. So that's one of the goals of this. That's not the firmware case, but it's a case we care about. You do have to rearrange paths just a little. So by convention, init is /init, and we are gradually moving to be /Linux underline architecture name /init. So we get this thing, throw it into any of the machines that Go supports. You can boot that machine. Now, recently, even though I'm really pretty big on having the source in flash in the file system, I did get a request for compress all the commands into one binary and just put it in a very small flash part we have, and don't bring the source along. So in fact, in one case, somebody wanted to not use fork and exec. So you boot a kernel, you boot a program, and that program is used to boot other programs, other kernels. They wanted fork exec not to be an option for security reasons, so we've enabled that. But in general, the thing that I really care about is the dynamic compilation and all sources there. The other thing, though, is when we do all these crazy variations on this theme, we don't go back and rewrite commands as people have had to do in the other worlds. You know, BusyBox is essentially a rewrite of all the bin utils in a more compact form. We don't have to do that. It's always the same source. It's just the way that we sort of do the transformations on it to produce the variations. So here's an example of some of the variations. The one at the top we call max, and that's mainly what the paper is about. Currently, there are 5 binaries per architecture. All the commands are in source form. We use dynamic compilation, and we have multiple architectures in one device. And you can see some different variations. The green is slightly more compact. The bottom green line is what we call the pre-boot model, where you'd be in firmware. It's for one architecture because you don't conventionally have different, have a firmware ROM for different architectures. So there would only be really 5 binaries because we're only going to boot for an x86 or an ARM or something. And then at the very bottom is quite minimized, where it's one binary. We don't do fork exec, and we've jammed it into a very compact firmware place. So I want to talk mainly about max because that's what the paper is about. You've got to have a kernel because you're going to boot. There are 5 or 4 or 2 Go binaries per architecture. This used to be an easy answer. How many Go binaries do I need in a tool chain? They keep changing it because they keep making it more compact. In the last October paper at the Embedded Linux Consortium or Foundation, there was a Go compiler, a C compiler, an assembler, and a linker. Go's gotten rid of the C compiler that they used to use for some of their source. So the Go C compiler went away. So then there are the Go compiler and assembler and linker, but now things are changing, and it's beginning to look like you can produce sort of the code for any binary from a single Go binary in some cases. But let's go with 5 binaries and be honest now. Then there's the uroot source. This all compresses down to 13 meg in flash. And we mentioned in the paper we booted this on a couple of different x86 hardware boards, and you can test it out with the Docker repo if you pull it down. So when your kernel boots, and this is when I say kernel, I'm following the convention, which is there's only one kernel, it's called Linux. So when I say the kernel, I mean Linux. So when Linux boots and it unloads the init RAM FS into memory, you kind of get up this structure shown here. Now maybe in uroot max we'd have the different inits at the top that we've compiled for the different architectures. In the middle, there's the uroot source in yellow, and you can see there's source commands, things like dd and cat. GitHub.com, those are packages we brought in from elsewhere that we compile. You can see the Go source in green, and you can see the Go package directory there, and the Go packages are compiled on demand, so that's essentially empty. And then finally at the bottom, I'm not good with colors, right? But the slightly lighter green is the components of the Go tool chain. So that's what it looks like after boot. And notice there's really a binary that's going to run init. There's no shell compiled yet. So init has some work to do. Init builds a directory called builtin, populates it with links, one for each uroot command. The links point to a thing called install command. Init builds the install command. It creates an empty bin directory because we don't have binaries yet. Then it fills in some things like etc dev and proc that have got to be there. You've got to have a dev null, for example, or you can't really run the Go toolchain. So you get this kind of root file system that's ready to use, and then the final thing init does is exec sh. And notice there is no bin sh, and the path is arranged so that build bin is the last thing. You crash all the way through to build bin sh, which is a link to install command. Install command gets run, looks at its first argument, says, I need to build bin sh. It builds it and execs bin sh. So you kind of come back around behind yourself and exec the thing you were asked to build. And that's basically all there is to it. And I note that because of the way Go programs work, every program has a set of import statements that name the packages that it's going to use. Those packages may import other packages, so you can pretty quickly sort of compute this transitive closure, figure out what you have to build. The go build command will do that for you, and then you end up with all the packages you need built, and then your program is built. So that's kind of the first level, right? That's where we got a bunch of programs we've written, cat, dd, cp, sh, whatever, and we kind of dynamically compile them and run them on demand, and that's kind of step one. But you've got to have scripting, and you have to have built-ins, and of course nowadays, you've got to have functions in your scripting language or people are going to be unhappy with you. So the shell that comes with uroot does have the ability to take a file filled with basic commands. The commands can be compounds or pipelines or whatever, and it will run them. But we don't have the ability in the uroot shell to do functions, and that was a deliberate decision There have been so many exploits in the last few years that involved broken shell scripts that we decided we weren't going to go there. And we decided that our shell scripting language, in fact, was going to be Go. So that way we've got one language for our tools and our scripts, it's Go, and we have one language for built-ins, which is Go. So it keeps life simple. So we use Go to write Go. We use it for scripting, we use it for dynamically creating new shells with built-ins, and we use it for creating the small memory precompiled versions of uroot. So here's an example of a script for the IP link command. Those of you who've seen the IP link source, you know that it's a bit bigger than this, quite a bit bigger. Things to note, the command to run a script is called script. It's compiled dynamically when you type it, of course. That left curly is the way we indicate that this is a Go fragment to the script command, and then that's just regular Go code. Important thing here is net is a package, and it has a function it provides called interfaces. And to really make this work, you've got to decide that's a package, not a variable, and then you have to determine that interfaces is a function that really is exported by that package. So this isn't sort of a textual thing where we say, oh, they said net dot something, we'll throw in a thing to say import dot net. You've really got to look for the package, make sure you've got it, and make sure interfaces is a function in that package. This is a semantic level analysis. Next thing, we get that v colon equal, that's kind of a declaration and assignment. V gets a variable from, of a certain type from that package. And then we dereference v with that address function. And again, as you look at that, you've got to determine the type of v and the fact that there is a thing that you can invoke using v called address. So there's a bit of work here, but when you run that script, you get that at the bottom. It shows you the two interfaces and the two IP addresses on each interface. And note that I didn't have to think about how to format this stuff. I tell Go %v, and it says, fine, I've got kind of a way to turn that thing, whatever it is, into a string. And I don't think about it. If you've looked at the IP command source, there's a huge amount of effort that goes in there and kind of pretty printing things. And maybe this isn't the prettiest printing, but I didn't have to think a lot about it. So script reads the program. If it sees a curly, it says, you've said curly. I know you really want to have a func main. So it puts a package main. It throws a func main at the front, passes it onto this thing that uses the Go AST package to parse the program, find the package usage, validate that all the use of packages will work. So as an example, if I had said net dot something or other, it would have decided that that didn't even exist in the net package, and it wouldn't actually generate an import net statement. I'd end up with an invalid program, essentially. That's how you find the errors. And in the end, I got something like this. So the package main was put there by the script command. The import net and input format was done by the thing that uses the abstract syntax tree package. The dot dot dots are that little Go fragment I put in. It builds it, runs it, you're done. You've got your command, your little built-in. And that could be in a file or whatever. Built-ins, you need to go a little deeper. So normally built-ins, of course, extend your shell code with this interpreted stuff. And if you're familiar with the sys5 init scripts, what happens is you see a file include a bunch of built-ins, and then you see the next file include the same bunch of built-ins, and so on and so on. And you actually trace it. Can be 10 to 20,000 file includes of scripts in the sys5 init scripts as they run. There's just a huge amount of this. It's one reason they're slow. What we do instead is we actually recompile a new shell with the built-ins you've specified. That also takes only a second or so. So here's what a shell built-in can look like. In this case, I'm naming two built-ins. One's called hi, one's called there, so that when I get the new shell, if I type hi, it says hi, and if I type there, it gets there. So in this case, I basically, the Go fragment is a single argument in the quotes, and hi is the name of the command, and there is the name of the other command. So a quick digression into what built-in source looks like in the shell for those of you familiar with Go. This isn't super important, but basically a built-in is in package main because it's in the shell. It imports some things. The init is kind of like a constructor. It gets run in file scope when you start the program, and that's calling a function called add built-in. It's mapping the name cd to the function below called cd. So this isn't that important in terms of the structure, in terms of what it's doing, but in terms of the structure, you need to have the right import statements, you need to have an init thing, and you need to wrap that little Go fragment with the right kind of function declaration. So how do you customize a shell in a few steps? So you create a unique tempter, you copy the shell source to it, it's in source/sh. You convert those Go fragments in that built-in command to real, actual built-in files as the form in the previous slide. You create a private namespace with a new /bin. Oh, that went fast. Okay. You mount, bind, attempt, or resource commands sh. You run build, and you just run build bin sh. So right up to the almost the last step, it's a little special, and after that, it's not special at all, right? Because it's just the normal uroot flow. It's just that the source just changed. The sh command is gone because you've mounted your tempfs over the existing bin. You've got a new shell. Child shells will get the built-in. So in that sys5 init scenario, what you would do to get the scripting for sys5 init scripts is you'd set up the new shell with the new built-in once, and then everything after that, under that shell, would get the new shell. You never have to source all those files again. Nobody outside your private namespace sees those built-ins, and when the shell exits, the built-ins are gone. So these are actually a lot more efficient. You've got a statically linked shell and a init-ramfs. Starting the shell is pretty painless in terms of performance. There's one little bit further that we've taken the rewrite. I don't know if anybody here has ever used a QB board. It's a wonderful little board. It's $130 or something. It's got an all-winner A10. To get an idea of the scale, that little board, the top left thing there is an Ethernet jack. So it's tiny, right? It's very low power, nice board. It's also slow as can be. You do not want to do dynamic compilation unless you've got an extra 40 seconds to wait around for stuff to start, right? So, we had this request, can you please just not do that dynamic compilation for some of these targets? And we said, okay, well, we held our nose and had to do it. So here on the left is kind of the skeleton of the ls command, and all we really have to do using the AST package is rewrite the package name to ls. So every command becomes a package. Because of possible conflicts in the arguments, we kind of internally change the string L to ls.l, so we have to somehow root that. We hide that. You don't have to type ls space ls.l. We kind of hide that transformation at runtime. And just for fun, we turn func main to func capital M main. And at that point, the shell's got a built-in called ls, and just repeat for every other thing. And then you root as one program. No special crazy linker fun. It's a about 130-line program to affect this transformation. We can actually remove the need for fork exec, which we've been asked to do. The Go size penalty, which a lot of people complain about, I understand the reason, but one program is 2M. It's a high-level language. You have to pay. 33 programs are 7M. It compresses to 400K. Things that come with it are DHCP, wget, ping, stuff like that. And the goal of this, basically, with this system is we can wget something, we can verify the signature of that something, and we can kexec that something. So we're booting a kernel out of flash. We're starting up this very combined sort of uroot command shell. It's going to suck down the new kernel, so it's got to configure the network, do a wget, verify the signing, call kexec. Those are all commands that are in uroot now. And that's our bootstrap mechanism. It's not grub, it's not syslinux, it's Linux with commands that are familiar. Processing all the 33 existing uroot commands takes about 0.2 of a second, and a full build takes 12 seconds, and actually runs faster than a configure script on almost any of the 512 packages that comprise Chrome OS. So it's pretty fast. So why do this? Why did we even start this project? We think we can build safer startup environments for things like, in my interest actually is in doing this for Chromebooks, but for a lot of other embedded stuff. Writing in Go instead of C, I think, is a huge step forward. It avoids all the many problems that come with writing in C, all the errors that we all commit. If anybody's ever watched Coverity run across their code base and discovered all the things that you managed to get wrong. We can verify the root file system. Root file system is now really tiny, and we can use a very long key instead of just doing block by block verification. It's a much easier embedded root to build and work with. I can tell you from experience, having done a lot of that with BusyBox and ONIE. And in the one case, in the not so compact case, you can see all your sources. And the final thing is, it's nice to know how things work. So if you ever wondered how the IP command works, you can look at the IP one in source, and it's just gigantic and hard for me anyway to understand. This one, I believe, is a lot easier to work with. So that's the how to get it, and I am done. Any questions?
Just simple, stupid question about the privileges of the shell. I mean, if you are trying to run ls in command,
yeah,
and if you want to do sudo ls, then is it forked or?
Oh, I haven't implemented sudo yet.
Oh, okay.
But actually, in a lot of these cases, you're really root anyway. You're booted from firmware. So you've come up and you really only have one user identity at that point. There's not even an etc password in this system. But
Okay.
I think it's a good question. It's something that we need to look at doing. So, but haven't thought about it yet.
Okay.
Thanks.
Justin Kapos, NYU. So the technique that you're using to go and replace the imports and look at what's happening that deals with the AST doesn't seem like it would work for dynamic code that has some kind of dynamic decision about what to import, which happens occasionally in like Python programs or things like that.
Oh, yeah.
I'm just curious, is that something that you ran into at any point, or?
No, because the language itself is pretty, well, the main thing is the way in which we make those dynamic decisions essentially would be to generate a new thing, compile it, and run it.
Mm-hmm.
So that's the emphasis. So there's not that sort of at runtime interpretation of importation. It's the at build time, which is why this is a great question. This is why it was so important to us that the compiler be fast, because we don't have that ability to make that decision at runtime, essentially. It's a good question. Thanks. Yeah.
Last question, Brian Dorsey from Google. I'm coming at things from a containers perspective, but also talking to other folks who are doing virtual machines. Having a smaller image seems to be the key to having fast boot. You know, and it seems like this could be used as an execution environment for user programs, perhaps arbitrary user programs that you're running in a container.
I agree. In fact,
your Docker example proves it works. But
do you know Minnix?
Not in much detail. No.
Okay, so I've ported process Flask.
Okay.
So pflask runs.
Okay.
And I am always looking for people to help improve and write new code. So I hope you'll come find me.
Awesome, I will. Thank you.
Thanks.
Looks like it's